Hey everybody, we have today is a failed Cree light bulb. This is the BA19-08027 OMF. It is a I think that says 9.5 watts. I don't know, it's kind of hard to read. Maybe you can make that out. But it didn't last very long at all, not even a year, and it hardly even ran. But luckily Cree's a good company and they are sending me another one in the mail. I've already started here before I thought to start the video. And I just took off the bulb base part here, and I did that using my usual technique that I use on CFL bulbs, where I take a razor knife and I cut into it to get it started, to just get a little hole in there. And then once I get that started, I take the screwdriver, flat blade screwdriver, and I stick that in there and pry that up. And then once I can get this a cut up the edge here to where it's loose and it comes right off, then I take I either use a torch, or usually what I do is I take it to the stove and I just heat the bottom here with the stove, and that melts that solder, and then that just pulls right off. And on this one, they actually went to the trouble of soldering the other wire too, which is right there. And I melted that with the same torch, and that just came right off. So you can see the circuit board in there, and they use some kind of silicone around here. And it's very flexible and it peels right off, but yet that is really on there. I can't get that off. So that's going to be my next course of action, because this board does not just slide out here. And this is loose, but for some reason it won't come off. So I'm going to have to work on this some more, and we'll see how this progresses. I'll pick up the video when I get this further apart. Okay, picking it up here, I got the board out, and how I did that was, and this took a surprising amount of force to get this out, but I had to take a small screwdriver that would fit in here between these fins on this heatsink and pry up in here so I could get under this plastic thing. I tried cutting into the side, and this is like ridiculously strong plastic. I could not. I actually broke my razor blade, but trying to get that out. But the screwdriver trick worked. So actually it had to break off some of these tabs. They like went up into this silicone here. So they were really in there good. And then once that came out, the board just slid out through the top like that. And then once that was off, I could get my other screwdriver into one of these holes and then just pry like that, and the silicone came apart. And now we have the LEDs exposed. There's 10 LEDs, and it looks like they're all in series, which makes sense, because this is just all this is just a simple buck driver. I was really surprised, and it's mostly all on the one side, and they didn't even solder the LED string onto it. There's just like 2 tabs in here that when the board goes in, they go onto these 2 large pads here to make contact with the board, which I thought was kind of interesting. And the LEDs are on looks like an aluminum core circuit board that's been bent around this heat sink. And that's how the heat travels from up here where the LEDs are down and then out to these fins here for cooling. So that's, yeah, I was surprised. I thought maybe there would be a transformer in here to step the voltage down, but no, it's just a buck driver. These are just coils. There are only two. There's one up here, probably for line filtering or PFC, and then this one here, which I assume to be the main coil for bucking the voltage down. And it would make sense that these would all be in series. So 10 of them in series, say 40 volts a piece, or 4 volts a piece, so that would be about 40 volts. So that's it's actually fairly standard for these things. So I'm gonna get a little further into this and then we'll pick up in a minute here. Now, taking a closer look at these LEDs, you can see, I could see, you can't see it, but I could see that these are, not only are all 10 of these devices in series, but inside, if you look closely, each one is actually 8 individual little wafers in series. So these are a special LED. I did some probing on them, and I got them to light up, and they don't even come on until about 19 volts, and they start to glow decently at about 20 volts. So that means this entire thing here runs at over in excess of 200 volts, which is pretty, I find pretty amazing or unique, or not the approach that I would have expected. But this is the first one I've ever had apart, so maybe this is common in the industry, I'm not sure. Very interesting to me. And so the thing that I don't like about this is a metal core circuit board sitting on an aluminum heat sink, cast aluminum heat sink. And so the only thing separating you, and this, since this is a buck driver, the circuit in here is actually tied into the AC line. So the only thing preventing you from getting a shock is this tiny little, like, painted on layer on this circuit board and the paint on this heat sink. So otherwise, if any of that had failed, you'd be at over 200 volts. And plus, you know, whatever is coming out of your AC line. So if you're in the US or Canada or Australia, that'd be 120 volts AC, or other parts of the world it'd be even worse. It'd be sitting there at 240 or even more possibly. So that I didn't like too much. So I tested all these LEDs and they all still work, which doesn't really surprise me in such a young light bulb. I mean, this thing has barely been used. So that leads us to the driver. Something on this driver has failed. And it is, I was looking at it, and it is a buck driver too, because this is a 315 volt capacitor. So that, I didn't look really close. I mean, I didn't trace it all out or anything, but just the fact that this is a 315 volt capacitor is telling me that this is most likely going to be a buck driver. So what it does is, I'm in the US, and so I have 120 volt AC line. So what it does is it takes that, doubles it to about 300 volts, and that's what's driving this buck driver. So it's still, though, it has to buck about 100 volts. So not quite, maybe not quite. So there's probably something else going on here too, but, well, no. Yeah, because there's a capacitor. There's a fairly large capacitor. Let's see, what size is this capacitor? Yeah, this is a 220 nanofarad, so 0.22 microfarad, for those of you who aren't familiar with the SI system. So I think what they're doing is they're using this capacitor as sort of a what they call a transformerless power supply. So this eats some of the voltage, about 90 volts or 90 to 100 volts, and then this inductor eats up the rest, so to give you a constant current. And there's a small surface mount driver chip on here, and I can't quite make out the numbers in this light, but it looks like it's a ST. Looks like 6. What does that say? Well, there's two sets of numbers. One starts with an L, and the other starts with a 6, I think. So, and then the transistor. This is going to be the transistor right here. The main one is a 3N40K3. I can't quite make out the maker mark on it. Looks like that might be an ST as well. So it looks like maybe ST did the power supply for Cree here, maybe. We'll take a closer look at these things here. And, oh, I like this. There's nice little board art in here. That's what I like about taking things apart. Sometimes you get like a little Easter egg inside. Can you see that? There's a tiny little smiley face right there. So there's a little board art and Easter eggs going on in there, so that's kind of neat. And it looks like there is some kind of a barcode here resembling a QR code. It doesn't look like it is a QR code, but it's similar to a QR code. So kind of interesting. And I don't know if I trust this. Probably what happened, and I'm just guessing now at this point, but there's a 500 milliamp fuse right here, this tiny little surface mount fuse. Actually, it's pretty large. I've seen much smaller surface mount fuses, but I'm just guessing, but because I haven't really got into this and I don't really intend to, I'll probably just buy a LED driver on Deal Extreme or something to run this again. If I do, maybe I might even just throw it out. It might not even be worth my time, but something on this board has failed, possibly causing this fuse to blow. That's a lot of times what would happen, because this is just such a new circuit board. Probably something on here was a little weak, and so it just failed straight away. That's generally the way electronics fail. Either it fails when it first is plugged in because of some faulty component or an error during assembly or something, or it'll run for a long time and then die of old age when the components get so old that they're not working properly anymore. So let's take a closer look at these this control chip and this transistor and find out a little bit more about this thing. And it's also possible that there was some voltage spike or some transient on the line that got into here and either caused the fuse to blow, which I've seen that before, or it got into one of these components here, possibly this capacitor, which is directly across this thing, or one of the diodes. There's a tiny little diode bridge on here. Right there, you can see it under this capacitor, and caused that to fail, and then that popped the fuse. So it's either a transient on the line that caused the fuse to blow, or just one of these components in here, because this thing is completely dead. And I'm betting that if I do a continuity test on that fuse, it'll read open. I was able to pull up a data sheet on the main control IC. It's an L6562A, and I was surprised to see that it's actually a PFC controller. It's not even what I thought it was, like a SMPS controller or a buck regulator or anything like that. It's not really designed to drive LEDs, and not even designed to act as a buck regulator. So they have adapted this quite cleverly to work as an LED driver. And I'll link to the data sheets and everything in the description so you can take a look at them yourselves. But it's just basically, it gives a few examples, some performance curves, and basically how to use it as a PFC controller. But I'd be really interested if anyone has the schematic for this actual driver. I'd really be interested in taking a look, because I tried tracing it out and I didn't have much luck. It's kind of convoluted, you know, it's a double-sided PCB, so it's kind of tough to figure out. I'd have to wipe all the components off and rip out all the through-hole parts and everything to get a real good look. But and I actually checked the fuse, and the fuse is still intact, so I'm not sure exactly what happened. My theory is that maybe one of the diodes in the bridge. Sorry, I got a headache. I'm doing the best I can here. My theory is one of the diodes in the bridge rectifier is open circuit. Has gone open circuit. And I also found the data sheet for the LEDs themselves, and they're a Cree LED. Okay, here it is. It was right where I thought. They're the Cree XBG series, and if you look here, you can actually see the individual dies. There's 8 dies in each LED package. And again, I'll link to this data sheet in the description. You can see all the performance curves and everything, all that interesting stuff. And I was pretty much spot on. They drop about 20 volts. Actually, this says 25 at operating current. Actually, at 44 milliamps, they're already at 22 to 25 volts, but they're rated 200 milliamps. So if you go down here to the curve, if I can find the right curve, one of these should be the current to voltage drop curve. There it is. Current forward voltage. So if we go up here to 200 milliamps, okay, 25. So the maximum rating up here is your forward voltage at your rated maximum current, 25 volts. So 25 times, there are, how many did I say, 10 LEDs in there? It's 250 volts. So fully rectified mains, or doubled mains I should say, is about 330 volts minus 250. So that actually that regulator has to drop about 80 volts, which explains why they used a buck instead of a linear, because 80 volts being dropped by a linear would be a huge power dissipation. So multiply that by 200 milliamps, and you see you'd have 16 watts dissipated just in the driver. So that's why they did not use linear there. I'm pretty sure all of the LED drivers that work off of the mains are buck, just because of that efficiency problem. They're either buck or step down. They actually have a little transformer inside. But this driver here is very clever. Whoever designed this was way above me. I mean, this is genius. This here, to get a buck driver out of a PFC controller. That's just incredible. And it does. It actually, there was I found a forum. I don't have the link to that. If I do find it, I'll post that in the description as well, where they actually went and had a waveform of the output of this driver and the input on an oscilloscope curve, and it actually was doing PFC as it was bucking. So it's just pure genius, this thing is. But obviously the failure was not due to poor design, because I couldn't find anyone online that had actually had one that failed. So these are very good design. I think I just got a poor component, or maybe it got ESD damaged during handling, or overheated a little in the reflow process. I'm not exactly sure, but or if it was, maybe it was just bad from, it was just barely working from the factory. So anyway, that's your newfangled LED light bulb, Cree LED light bulb. Marvelous technological prowess going on here. I hope you enjoyed, and I hope it helps someone out there. Thanks for watching. What am I trying to say here? I gotta take a crap. Crap. Great timing, asshole. Right when I'm in the middle of something is always the way. You can see that these are, not only are all 10 of these little units, what's the word I'm looking for? Whoops, I didn't want to do that. Where are they? X lamp. Maybe I know where it is. Well, I guess I didn't save that. I should have saved that for you. I swear I had it saved here. Well,